right, so one of the interesting things about using technology is that sometimes things don't work. So I cannot tell you what happened. All I know is that there was a score that was given to you at some point right after you took the test. I didn't ever see those because I didn't look because I didn't have time. So I was getting all this other stuff done. And I sat down to look at it this morning. And my understanding is that things shifted at some point in the morning. I don't know. Is that what, because I talked to your mom about this and she said that you heard different, like you had a different value that came out or something like that? A different score. Is that true, Kian? Yeah. So anyway, I don't know what happened because I went back to look at it during my third period plan today and to make sure that I hadn't messed anything up because, like you all know that I'm human and I mess things up sometimes, right? Like I totally do that. I had intended to click the off button so that you wouldn't get scores, and I thought I did, but I must not have hit save. Like, moral of the story, make sure you hit save. So this wouldn't have even been a thing. But apparently I didn't. But apparently Canvas did something crazy too because things changed before I had time to look at them. So I don't know what happened. I don't know where the glitch happened. Like, it was not, like, it didn't happen right here. I don't know. I mean, in terms of, like, I hadn't changed anything when the things changed. So anyway, I have all of the data now, and I've looked over things. And there were some questions that everybody did really, really well on. And there were definitely some questions where there was a wide spread. Part of the reason I like doing it on Canvas is that then I get data so it tells me exactly what percentage of you said A and B and C and D. So I don't have to do that math myself because that's a lot of work for me. And I honestly don't have time to do it. So I can see that. So I can see kind of where mistakes may have happened. And I looked through it. I spent some time pouring through it. And the questions that were commonly missed, I will be honest, I'm not surprised were commonly missed. Does that make sense? They were ones that like had two answers, both of which one might be able to convince themselves of. Okay? I don't think they're bad questions, but I think that they're learning opportunities. So we're going to do the same thing we always do and do corrections, just like we normally do. And if you have questions, you want to go through things, like I'm here and I want to do that. The weird little hang up is that next week we don't have Liberty time because we have ISASS tests, right? So I just want to make that really clear. So you find a time to come in when it works for you. If you want to talk to me about it, I'm available 3rd, 7th, before or after school, okay? Those are the times that I'm not teaching. But if you want to come in with another person, friends, could you be quiet just so that you don't have to ask me these questions again and I'm not distracted? That's okay. I'm just letting you know. So now we're on the same page, right? Sweet. I want you to go through them because I want you to see if there were mistakes where they happened. Does that make sense? Okay? But I think that overall things should be right now. And if you feel like something happened, let me know because I'll go back and double check, right? Like maybe something got clicked funny. I think that we're all at a good spot right now, though. Does that make sense? I don't know. Or I should say we're at an accurate spot right now. Question.
Oh yeah, so since we're on the return next week, is it fine if we get it done by the week after that?
I mean, I guess. Like it's kind of I don't want to draw it out forever. Let me put it this way. Or I'm still on freeze. Hold on just a sec.
I won't be here Tuesday.
No, it's all good. I'm just gonna tell you kind of where we're at. Come on, team. There it goes. So my answer is kind of a short and long one at the same time, Isaac. So this is the calendar. I don't have the homework put in yet, but this is the calendar for the next unit. It's a short one. Boom. Boop. Okay. So my intention is to test not next week, but the next Tuesday. Okay. The reason for that is not because I'm trying to stress you out, but because do you see what happens 2 weeks after that? That's the big one, right? That's the AP test. So I want to make sure that we have 2 weeks to review, okay? So my intention is for us to test over circuits on the 23rd. The only reason I'm telling you that as part of your answer or the answer to your question, Isaac, is that that's going to be, then you'll be doing your corrections over the circular motion stuff after you've taken your other test. Does that make sense?
Yeah.
But if that is the time that you can make it work, I'm fine with that, okay? Because honestly, at this point in our physics career, in the next 3 weeks, 4 weeks, whatever we're at, we're just really focusing on May 7th. And so if that's where you're going to get your review, then that's cool with me. Question.
Is it going to be a 2-day test again for the final year?
No, it will be a 1 day.
Okay.
Wait.
On the 23rd, is that what you're asking? Yeah, the 23rd will be a 1 day test.
Okay.
And then we'll be reviewing. Yep.
Yeah, some of the band leaves 24th
Okay.
for the band trip.
Okay. So you guys will have to work that out with me later. Yeah.
So we have a final in this job.
No.
Oh, okay.
I was just going to say yes. All right. So are we okay with all this?
Just to clarify about the past test, so the grades that are in Canvas are the accurate grades?
They are accurate as far as I can tell without me having to go through and grade every single question. But if you feel like you want me to look at yours in particular, don't tell me right now, because I'm not going to remember between now and the end of the class. Send me an email and I can absolutely go back and look over your test in particular. Does that make sense? Yes. But I just kind of glanced over things and went through a few people just to kind of make sure, and it looked like they were accurate to me. Okay? So, yeah, so yes with an asterisk, I guess, next to it. Okay, so we all good there? Issues, questions, concerns? All right. So you may or may not be aware that 2 days ago we saw for the very first time pictures of a black hole, which is a super huge big deal. Super huge big deal. So I have a quick, short 6-minute video that I want to share with you about how it happened and what's going on. So I'm going to get it started here and turn some volume on.
What happens if we go into it?
We can talk about that in a second after this ad. All right. Shh. Friends, pay attention.
A group of telescopes on mountains across the planet switched on at the same time. For the next week, they danced in unison, collecting radio waves dispatched from the center of our Milky Way galaxy and from the galaxy M87. Together, they make up the Event Horizon Telescope, a global project to capture the first ever picture of a black hole. That's right, ever since physicists first conceived of black holes centuries ago. Every image of one from our textbooks and our space agencies, they're all illustrations. Until now.
We are delighted to be able to report to you today that we have seen what we thought was unseeable.
For centuries, physicists have theorized that an object with enough mass and density could trap even light in its gravitational field. Just as you have to travel faster to leave Earth than you do to leave the moon, there could be a place where you'd have to travel faster than the speed of light to escape, and nothing moves faster than light.
Pause it right there, just because this is what we just tested over, right? This gravitational field business. Okay, so I just want to put this in your head, and I think for most of you, you get this, but sometimes just kind of repeating it and understanding it makes a big difference. So you know that if I wanted to launch something into orbit on Earth, I'm going to have to throw it with a whole lot of velocity, right? Like if I take the frog and I'm trying to get him to orbit, I'm going to throw him really hard, really going fast in order to get him to orbit or to leave the Earth's gravitational field, or to get far enough out that he's not really in it anymore. Because remember, gravity goes on forever. So everything is being pulled on by the Earth, but just not very much. So the gravitational field of Earth is pretty strong. If you go to the moon, if you ever watch videos of people walking on the moon, right, they go, wee, wee. And the reason they do that is because they're just walking. It's just that the gravitational field of the moon is smaller. We know that that's not a surprise, friends. If we think about it, like I really want to think physics here for a second, Fg equals gmm over r squared, right? This is the force of gravity between the astronaut and the moon. So one of the masses is the mass of the moon. Second mass is the mass of the astronaut. If I want to talk about the gravitational field, really what I'm talking about is little g, which is big G, m, so that's the mass of the moon, over r squared. The mass of the moon is much smaller than the mass of the Earth. The radius is smaller as well, but the mass is so much smaller. This is a much smaller number. Okay, so the gravitational field of the moon is much smaller than that of the Earth. The gravitational field of the sun is much larger than that of the Earth. Okay, but there are things like comets that have enough speed to escape the gravitational field of the sun. Okay, it's all about how fast you have to go. We could do the math to figure out how fast you have to go, okay? The trick is that for something as dense as a black hole, the mass is ridiculously high and the radius is ridiculously low. If this gets really big and this gets really little, this gets really, 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 really big. And that means that the escape velocity, that's how fast you have to go to escape the gravitational field, goes to the speed of light. Okay? If it's at the speed of light or over, then nothing can get out. So it doesn't matter how fast I throw this frog, there's no way he's going anywhere. He's just going to fall back down into the black hole. Yeah.
So like a black hole is super dense, right? So
Super dense.
okay, so like how would it be physically? Like they say it's a black hole, so like it's a hole. I'm assuming like it goes through a hole. But would it
So
be
that's a
like an
misnomer,
actual
really. It's an actual, they're going to talk about it a little bit more in just a sec. So it's an actual object. So we have stars, right? Our star is pretty normal. It's pretty regular. It's pretty on the small side of things, okay? And it pulls in the reason that it stays in the way that it does is because it's got radiation pressure pushing out and it's got gravitation pulling in. One pulling out, one pushing in. It's in equilibrium. It's like F net equals 0-ish, okay? If you then so our little astrophysics for you for the day, right? So our sun eventually is going to stop radiating so much it's gonna give off a bunch of the outer layers, okay? And then the inner core is going to fall down in on itself. It's going to create a white dwarf, which is a really, really, really dense star, okay, essentially. And so that's going to be really, 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 really dense. But our star isn't big enough to make a black hole. If our star was, I can't remember exactly what the number is, but a few times bigger than it is, right? Some, tens or hundreds of times bigger than it is, then it would be big enough that when it got rid of that outer stuff, the inner stuff is going to fall in on itself, and the acceleration is going to pull everything in so much that that object can't let even light out. So it's an object, it's an infinitesimally small space because it collapses down to a singularity, right? One little point. We don't have any idea really what goes on there, right? Physics doesn't really work in that space, unfortunately. At least not the physics we know and love. Yeah. All right, let's keep going.
Rudy's been there. Interstellar explains it.
Was Interstellar Rudy, is that like a story about you? Is that your...
And light.
Yeah, it's amazing. All right.
The math from Einstein's theory of general relativity describes an area completely invisible to us within a boundary called the event horizon. And at the center of that black hole is a singularity, a point of infinite density, which is where physics as we know it breaks down.
They showed up in the math long ago and they kept reappearing and they sort of persistently would not go away. But Einstein always thought that there must be some physical mechanism that prevents stars from collapsing to an infinitely small point, which is actually pretty reasonable. I mean, because it sounds insane.
Eventually, scientists began to see things that only made sense if black holes were real, like the orbits of these stars around the center of the Milky Way galaxy.
Watch this. It's cool.
You see these stars just slingshotting around an invisible point.
So do you see all these little stars are moving, right? And they're like, when we watch or when we kind of imagine what's going on in our solar system, we have the sun in the middle, and then everything kind of goes around the sun, and that makes sense because we understand that because of this, right? But now we got these things that are orbiting nothing. Like it appears that there's nothing there. There's no star that I'm looking at and seeing and going, wow, it's so bright, right? There's nothing there. So the only way that we can really explain that maybe is that there's this black hole, this thing that we can't quite see.
And the black hole is the most likely explanation for putting that amount of mass in that small space for something that's completely dark.
And so they use circular motion to figure out how fast this thing is going,
that spirals
how much
around black
mass
holes.
has to be there.
Friction heats this matter up tens of millions of degrees, and anything that hot emits X-rays that we can detect with telescopes that orbit above Earth's atmosphere. This is a pair of galaxies that pass through each other. There are at least 9 suspected black holes here, but you can only see them when you look at the X-ray layer. These dots are X-ray sources linked to suspected supermassive black holes at the center of galaxies 3 to 10 billion light years away. And that's just from this small patch of sky.
Okay, so I want to point this out. So these dots, these blue dots, right, are X-ray sources. How far away did they say?
3 to 10 billion light years.
3 to 10 billion light years. That means that the light, and it's X-ray light because X-rays are just a type of light, has gotten to us, but it's taken 3 to 10 billion years for it to get here. So that means it's pretty far away, right? Okay, so it's pretty far away. And, you know, there are a dozen or so of these in this little patch of sky. And this little patch of sky is not the entire sky. That's the thing that I want to point out to you here. So this is like for scale, right? If you look up and you see the moon, and you look at a little patch of sky right next to the moon, just like about the same size as the moon, there are like a dozen or so of these black holes, supermassive black holes, right? Like there are a lot of these things. It's not like it's just like few and far between. They're all over. It's weird. I saw a hand somewhere.
Wait, so 3 to 10 billion light years, explain that again.
So a light year is the distance that light can travel in a year. So does that make sense? Do you want me to say a little more about that, or is that okay?
No, that's fine.
Yeah. Right. So we're talking really now. There are things about how the universe has been expanding, so that kind of changes scales a little bit as well. We're not going to get into that right now, but that's a whole different piece of the puzzle as well. Yeah.
Wait, like they're so far away that like that's not what it would look like now, probably, right? Like in
Of course not. Yeah.
in real time.
Yeah. Of course not. No.
Yeah.
They. Well, I mean, so there's. How do I say this? We don't really know what happens to a black hole as it gets more and more massive, except that it gets more and more massive. So the black holes are still there, certainly, and they're still giving off those X-rays because what else is a black hole going to do, right? Like it's already an exploded star. Like we don't really. So they're probably still there, but like the other stars that are orbiting them are gone.
Like if you were standing on a planet way out there, like
Right.
yeah,
Sure.
you wouldn't be able to see the Earth.
You would see what was here 3
Yeah.
billion years ago,
That's weird.
right? So you're looking back in time either way.
Yeah.
Yes.
So you can time travel.
Yeah.
Well,
No. That's the problem. I mean, like, that's the fundamental problem of why you can't time travel. Because it takes time for light to travel. So you can't be in two places at once. It doesn't work. Right. Yeah. So like the first 2/3 of Interstellar is good, and then the last third is like,
no.
oh.
Okay. It makes
I don't want to go there. Let's keep going.
Some supermassive black holes also feature gigantic jets of particles, seen here in radio wave data from the galaxy M87, which has a much bigger black hole than the one in the center of the Milky Way.
I'm going to pause there for just a second. So have you guys heard of the Messier galaxies? So if you've ever like done any looking at astronomy or like started looking at galaxies, there are all these labeled galaxies, M1, M2, and one of them is called M87, right? And it's a galaxy that's far away from us, but not like super crazy far away. And it's got a black hole at the center of it. And that's the one that we took the picture of. By we, I mean humanity, right? Not me, just to be clear. Right? We have a black hole at the center of our galaxy as well, as does Andromeda. So Andromeda's up in that poster right up there, okay? At the center of Andromeda, there is a black hole. Oh, okay, so like we can see it, but there's so much stuff around it, so much stuff that is orbiting it, and that's what we're looking at. The cool thing here is that they were able to zoom in to actually see the black hole itself.
No other known source of energy could power these things.
5,000 light
And
years.
nothing we
that
know of
little
besides
spit.
two black holes colliding could have produced the gravitational waves we detected in 2015. Scientists think there are black holes, large and small, all over the universe. We can see their fingerprints, but we didn't have the mugshot. Directly imaging a black hole has been impossible because they're either too small, too far away, or both. Sagittarius A star, the black hole at the center of our galaxy, has the mass of 4 million suns, but it would fit inside the orbit of Mercury.
Okay.
Oh.
I just want that to sink in for you. Because we can measure the speed of how fast things move, right? I mean, literally, Isaac, your question is well stated, but this is the answer. The answer is right here. How do we know this? Because we can tell the mass and we can tell the radius because we can measure how fast things are moving around it, right? So 4 million suns in this space that's about the size of our sun. So what does that tell you about the density of this thing, friends?
It's fat.
Pretty big. It's pretty big, right? It's a pretty high density thing. Yes. All right. So taking a picture taking a picture of Sagittarius A, which is the thing that's at the center of our galaxy, at the center of the Milky Way, she says here is like taking a picture of, here we'll find out.
Imaging it from Earth is like taking a picture of a DVD on the surface of the moon, with huge clouds of dust and gas in between.
So many things had to go right
fairly
for this
difficult.
image to exist. So the first thing that has to happen is there has to be some slice of light that travels all the way from the edge of the black hole without getting knocked off course or absorbed by any of the gas or anything in between. And then it also has to make it through the Earth's atmosphere, which a lot of frequencies of light don't.
They landed on a wavelength of 1.3 millimeters at the high frequency end of the radio spectrum.
So we haven't really spent a lot of time talking about the EM spectrum because it's beyond the scope of AP Physics 1. We'll probably talk about it after the test. But anyway, so radio waves have really, really, really big wavelengths, okay? From on the order of football field size to on the order of millimeter size. So it's kind of a wide range of things. So the wavelengths that they used to measure to take the picture that was taken was 1.3, so about a little bit more than 1 millimeter, right? So just to kind of give you a sense, right? Here's a meter. Something that's about the size of your finger is about a centimeter, and then a tenth of your finger width. That's the kind of wavelength that we're talking about when we're measuring this stuff. It's in the radio part of the spectrum.
With that wavelength and with 8 observatories across the world, the Event Horizon Telescope had a chance at seeing a black hole, as long as the weather cooperated.
You have to have clear weather in all of those places at a time when the Earth is oriented in such a way that all of those telescopes can see the black hole simultaneously. They can really only observe once a year.
There was so much data involved that it had to be flown on airplanes. They waited 6 months for the hard drives to arrive from the South Pole, which closes during wintertime.
How often did he say that we could get data for this?
Once a year.
One time a year. Like, that's crazy, right? So not only is it one time a year, so it's one time plus no clouds, right? Or clear skies in all 8 of those places all around the world.
Don't choke.
Okay? Like, this is a hard thing to do. It's kind of a minor miracle that like that even happened, right?
Multi-telescope method is called Very Long Baseline Interferometry. It correlates time-stamped data from distant telescopes to boost the signal and quiet the noise. Each pairing of telescopes contributes a piece of the puzzle. But the image doesn't just pop out after that. They had 4 groups working for months to generate the image that best represents the data.
Okay, so I don't know if you, besides seeing the picture of the black hole, you may have also heard stories about the person who's kind of credited with this, right? So she was an astrophysicist that was a grad student at MIT a few years ago. She was the one that actually wrote the algorithm that took all of this data, right, that had flown on airplanes from all over the world to the United States, which is where they were kind of doing this. She's the one that wrote down, figured out how to program the computers to put it all together. But they say that they had 4 different groups doing this. Why 4? Why do we need more than one group doing it? Yeah. To make sure that nobody's screwing it up, right? Because if you have just one group, right, one really big group of people that all doing it together, oh, we got a picture. Who knows? Maybe somebody screwed something up. So instead, I'm gonna give you this data. I'm gonna give you this data, and then if you all come up with the same picture, chances are it's probably about the right picture, right? Whereas if you got 4 different pictures, then there's a problem there. This is how science works now. It's amazing. It's tons of people, lots of brains, but they do it in separate places so that they can compare to make sure that results are correct.
Each group was working individually and in isolation from the other groups, working with the same data to see that each group came up with the same image or not.
And the result of all that work is this.
It's so exciting. So exciting.
The bright parts are the
54
matter of light
million
swirling
light
around
years
the black
away.
hole, and it's brighter on the side that's moving toward us. And the dark part is the black hole's shadow, which includes the event horizon plus a region where light could escape but doesn't. The size and shape of the shadow appear to confirm the theory of general relativity.
Today, general relativity has passed another crucial test. this one spanning from horizons to the stars.
Humanity's first image of a black hole isn't crisp and beautiful like the illustrations or the movie Interstellar. It's better.
The picture we see this week is made of scraps and bits of light that's been traveling across the universe and collected by these, aluminum dishes on top of mountaintops and then combined in a supercomputer to make this image. So that's why it's real.
Which is, it kind of sounds goofy when he says it that way, but that's really what it's all about, right? Does that make sense? It's kind of cool. So, what's that?
How much does this cost?
I don't know. I can't tell you for sure. I know that people often ask questions like that, right? Like, what did this cost me, right? Okay. This is one of those things that goes beyond cost. Like, this tells you so much about the universe that whether or not it costs a lot of money or not,
Humans have to know.
it's not a thing. And we can have a philosophical discussion about that. Let's do it after the AP exam. I'd be very happy to engage in that conversation with you because I think that there's a lot to be said for it. But let's not do it right now. Is that fair?
Sure.
Okay. All right. Other questions about the physics or the science or any of that stuff?
It was 60 million.
There you go.
Do you have the full picture? Where's it?
That was the book.
No, there's another picture.
There's another one.
There's two pictures. That's one that's like really zoomed in. There's one
Sure,
that's
so
really
I'm
far
sure
away.
it's in there.
I mean, it would look. What's that?
They released pictures or
Okay. I just have that, and you could Google it too, right? Like just as well as I could. No, because we're gonna do other stuff. So you can Google it after class. Question?
So like you said it's a singularity, right?
Yes.
So that's like a super tiny thing, right?
Yes.
So is that at the center of the black thing in the picture?
Yes.
Okay. But that's not the whole black thing, right?
No.
It's not.
The singularity is infinitesimally small. Yes. All right. We are. Let's see. What time is it? Okay. Go ahead and write down a couple of things. You may want to write these down in some notes as well, but you don't have to. But I want your attention up here. If you don't get through all of this today, that's okay, because we're just going to keep cruising from here kind of throughout. It's kind of going to be self-paced a little bit here. So a couple of things that we want to note about circuits. So again, you can write this on your lab. You can write this somewhere else. Okay? The big thing that I want to get through with you right now is how to draw what we call a circuit diagram. So when AP Physics existed before they added AP Physics 1, we smashed so much stuff in AP Physics. AP Physics B, we covered everything from everything we've covered through all of electricity and magnetism, through all of modern physics in 1 year, and it was insane. And so College Board decided that they wanted to cut it in half, and that's where Physics 1 and Physics 2 came from. And they sat down, and it was like a 4-year process to figure out what was going to be in Physics 1 and Physics 2. And Physics 1 was supposed to exist without this unit. But there were tons and tons of people that said, no, we have to do circuits in Physics 1 because I want kids to see it. And this is one of the big reasons why, okay? It's because they want you, when you go into a physics class, if you say, yeah, I've taken some college physics, to know how to draw a circuit diagram. So that you don't draw diagrams like a kid would, but you draw diagrams like a physicist would, okay? So I'm imparting that knowledge to you today. Here it comes. The types of things that you have right now in front of you to make a circuit, what's one of the things that you have in front of you?
Battery.
A battery. And a lot of times for a battery, a artist's rendition of a circuit might look something like that, okay? And there's no judgment. I want to make that clear. If that's what you drew in your first part, that's absolutely fine. I'm not going to count it wrong. I don't want you to erase it. Like, I want you to leave it. Part of the reason I wanted to do it in this order is because I want you to have that experience first. So this is what a battery looks like when your average person draws a battery. When a physicist or someone drawing a circuit diagram draws a battery, it does not look like this, okay? One battery is going to look like this. Okay? With wires coming off of it. The long side is the positive and the short side is the negative. This is the positive side and negative side of an actual battery. Okay? If you have more than one battery stacked up, okay, so this is actually like a cell technically. Okay? You have multiple batteries stacked or multiple cells stacked up, that's a battery. That would be, or you could call it like a pile, that's another term for it. They go big, little, big, little. And it doesn't matter if you have 2 or 7 or 23. They don't draw 23 of these big, little, big, little, big. That would be silly. Okay? So it's either a single cell or multiple. And again, this is the positive side and that's the negative side. And we'll talk about what the positive and negative means later. We're not going to worry about that yet. Okay? But from now on, when you're doing these things and when you look at problems and things like that, you're going to know that if you see this or this, either one, you know that that means it's a battery. Okay? One down. What else you got? What else is in your baggie or what else are you dealing with in this lab? Light bulbs. So if you were going to draw a light bulb, it might look something like that. Right? Maybe you draw the little lines. Yay! It's lit. It's pretty. And this is beautiful. And friends, if you drew this, I'd say that's great. But the reason that I want to share this with you is because a physics professor and an electrical engineering professor are going to look at that and kind of snicker. And then they'll be like, oh, that's so sad. So I want you to know how a physicist or an electrical engineer, anybody that deals with these circuit diagrams is going to draw a light bulb. Generally, it's a circle with a little loop inside. Okay? What does that loop represent? The filament. The little wire. Right? Back in the old days, in incandescent light bulbs, that's the tungsten. Right? That might now be like an LED in there too. Yeah. You do not have to. It's just understood that the long side is going to be the positive and the short side is going to be the negative. And that will matter for us later, but just, I just wanted to clarify that for you. So that's generally what we draw a light bulb as, okay? What else? What else do you have in your picture? Wires? Yeah. And wires, so wires are lines, so you probably drew them as lines, which means that you're halfway there, right? But the thing is that when you have a diagram, or you have a diagram. So let's say that like maybe on that first one, your diagram looks something like this, right? So you've got your battery and you've got your light bulb and then you got your wires and they go like this, something like that. Yeah, look, maybe something like that. So again, we would change the battery, we'd change the light bulb. So here's the battery. Here's the light bulb. And the thing about the wires, this is the one that looks really not realistic. The rule for the wires is they have to be drawn with right angles. Okay? So they always, this is the cutest thing. Like I have like 2 people, they give me this look like, what? I don't know why. I didn't make the rules. I'm just imparting the knowledge for you. So it's going to look something like this. Okay? This is the circuit diagram equivalent for your pretty picture from number 1. Jonathan, you look really offended by this. I love that you've been like, you're just like, sure, like most of the year, like, and then you're like, no. Sorry. What did you just say? Well, it's because, the reason is so that anybody that can look at this same circuit diagram and everybody would build it the same way. That's the reason, right? It's kind of like how maps have certain characteristics that, most maps follow and that kind of thing. So this is the circuit diagram equivalent of your picture from number 1. On Monday, Monday probably, we're going to add one other thing to this, and I just want to add it now so I don't have to tell you later. And that thing is a resistor. Okay? And we'll get to know resistors really well. A resistor, we'll kind of talk about what they are later, but a resistor, honestly, is pretty much any other thing. Not pretty much. That's not really true. It's many other things that we're going to plug in instead of a light bulb. Resistors often, I'll go grab one from the back and bring it around so you guys can see it. They look like little, like, they're almost like peanut shaped. They're like little ceramic things and they've got stripes on them. We'll talk about that later, okay? But if you were going to draw a circuit with a resistor, you're not going to draw it like this. Number one, because it's really hard to draw that. Number two, because people are going to laugh at you. And I don't know what number three is, but just don't do it. A resistor looks like this. Okay? So it's just a zigzag line. Okay? So these are the 1, 2, 3, 4 things that for now I want you to know in terms of circuit diagrams. Does that make sense? Seem reasonable? To most of you, some of you are still a little upset, but we'll talk you down. It'll be okay. All right? You've got about, 5 more minutes. I want you to go through, make sure that you get through the front. If you've gotten through the front, work on the back. Get as far as you can on this today, okay? I'll give you a heads up in a couple minutes to clean up, but I want you to do your best.
We're doing 3 volts.